So this is my physical circuit that I managed to build out. There's my motor. I connected all the encoder cables as well as the motor cables and the power and the ground to be able to properly connect the motor. There is my MOSFET. There is my diode, which allows for one directional flow, and I used a breadboard to put it all together. And on my right, the power cable can be seen, 12 volts from the wall, which is powering this entire circuit. And my Arduino can also be seen in the video plugged into my laptop, which serves as the brain. And on my screen, you can see the basic Simulink model, where I am using a pulse generator to send an up and down signal alternating to the Arduino pin 5, which will allow me to toggle on and off the transistor, which will then toggle the motor to spin and stop, spin and stop. You will see the spinning in my next section. So this is my Simulink model for the step response. Initially, I started off with a simpler model, this one, simply to test the triggering of the motor, and it was successful. Then I moved on to the more advanced model, which is this one. So the way this module works is basically it's a Simulink program that implements a real-time motor speed measurement control using the Arduino encoder block interface that's available on MATLAB. And there we have the Arduino encoder read, which reads the physical encoder signal and sends a value to this variable that's called count. And then later on, we can use that to plot a graph. Then going on to this part, a digital pulse is constantly sent to Arduino 1, and this is the gains and the filters, which is used to improve the signal and the graph. Thank you. This is my motor speed step response with a filter, and the graph shows motor speed versus time. It essentially shows the open loop step response of the DC motor when a 100% duty cycle, meaning full input, is applied. And at approximately 1.1 second, as you can see here, the motor begins to respond, accelerating rapidly, very steeply when the voltage is applied. The steep continues up to 1.4 seconds, indicating a strong initial torque, and then gradually slows down towards steady state. The motor reaches around 63% of its final value relatively quickly, confirming it's a typical first order system. So I noticed that my RPM readings from my recordings were quite noisy, and I listed a few areas and a few reasons to ascertain why they were so noisy. Number one was the nonlinear friction effects, including static and Coulomb friction. Next was armature resistance variations due to temperature changes. Next, unmodeled electrical inductance and brush commutation effects. Then encoder measurements, noise and quantization errors, supply voltage fluctuations from the source under load, mechanical backlash and shaft misalignment, and lastly, simplification of the system to a first order linear model. Here is my Simulink model with filtering. As you can see, I created some filtering blocks to quote unquote clean the data, and here is the graph with filtering. And for a little bit of an explanation, I just measured the signal obtained from the step response contained, and I included PWM switching, electromagnetic interference, and mechanical vibration. And I chose a cutoff frequency to help improve the readings, and I did some calculations and it helped me to smoothen out the graph. I used the system identification toolbox to create a nonlinear ARX model. As can be seen, it's very smooth and ideal because it's unreal, but it's very, very idealistic. And I also created a transfer function model, which is a bit more realistic than the nonlinear ARX model. Lastly, I integrated PI, and PID control for the motors. I chose certain KP and KI values, which I deemed appropriate. And then I constructed my P response graph, my PI simulating diagram. I generated my PI controller response and my PID as well. And lastly, I graphed them all on one graph to compare and see what improvement can be made, which parts can be taken from which graph, and how I can overall fine-tune my system.